Alright, so in this video we're going to look at calculating equilibrium constant and writing our equilibrium expressions. So in the previous video about equilibrium, we looked at how the equilibrium expression comes about. Remember, we want to put products over reactants, and we only include gas or aqueous components. So in the first one, H2O2 liquid goes to H2 gas plus O2 gas. Our K equilibrium expression is only going to take into account the gas, so H2 times O2. We don't include the liquid. For the second one, we have 2N2O5 as a gas, goes to 2N2 as a gas, and 5O2 as a gas. All three components are gas, so we're going to include all of them. So first we have N2 squared, the coefficient in front of the nitrogen becomes the exponent, times O2 to the 5th power, and all of that over our reactant N2O5 squared, because it also has a coefficient of 2. So remember, all the coefficients become exponents for equilibrium. Alright, if we look at the third one, we have nickel nitrate. It's a solid. Goes to the nickel ion plus 2 of the nitrate ions. Alright, we're not going to include the solid. So for this one, our KEQ is just the nickel ion times the nitrate ion squared. Alright, our coefficient of 2 becomes the exponent. And we leave off the solid nickel. Alright, now last one, 8SO3 is a gas, goes to S8 solid plus 12O2, also a gas. So we're going to leave out the solid sulfur. So on top we have O2 gas to the 12th power divided by our reactant SO3 to the 8th power. Okay, so we're leaving out the S8 because it's a solid. Once we have our expression, we can use it to calculate either KEQ values if we know the concentrations at equilibrium, or we can calculate a missing concentration if we know KEQ. So let's look at the first one. We want to find the value of the equilibrium constant, so we're trying to find KEQ for our reaction below if N2O4 is 1.5 times 10 to the minus 3 molar, and NO2 is 0.571 molar. So these would have to be equilibrium values in order to find KEQ. So the first thing we need to do is write our expression. We're going to have NO2 squared over N2O4. Alright, then we're going to fill in our values. So NO2 was 0.571 squared, and our N2O4 was 1.5 times 10 to the minus 3. Alright, so 0.571 squared divided by 0.015 gives us 217.4 for our KEQ value. Alright, we can also use it to find a missing concentration. For our reaction, 2SO2 plus O2 gives us 2SO3. We know SO2 and SO3, but we don't know O2 concentration. We're given the Kc value. So this is a KEQ. Remember, measured in concentration units, so molarity. So we can use this to calculate our missing O2. So again, we're going to start with finding the expression first. KEQ is equal to our SO3 squared over SO2 squared times O2. Alright, that's our expression. Now we're going to fill in what we have. So KEQ is 800. SO3 is 10 molar, and it's squared. SO2 is 2 molar, and it's squared. And then here's our variable O2. Alright, so the first thing I'm going to do is move everything on the bottom over here. So I'm going to have 800 times 2 squared is 4 times O2 equals 10 squared is 100. Then we can divide by the 800 times 4. So O2 is going to be 100 divided by 3200. 0.03125 molar. So we can find our concentration for a missing variable. Alright, we previously talked about the difference between Kc and Kp. So they're both KEQs. They both represent an equilibrium constant. Kc is measured in concentration units of molarity, and Kp is measured in gas units or pressure units of ATM. Alright, so if we have one and we need to switch between it to the other, we can use the equation. So our equation, Kc is equal to Kp times RT to the delta N. Whoops, this should be Kp is equal to Kc. There we go. Let's make sure we have our equation right. Alright, so when we look at our first example, PCl3 plus Cl2 produces PCl5. We're given the Kc value 1.67 and the temperature. So by filling this in, we can calculate what our Kp would be. Now the other thing we need to know is our delta N value. And delta N is the change in gas moles between the products and the reactants. Alright, so let's do the first one and we can see what's going to happen here. Alright, we're solving for Kp. We know our Kc value. The delta N exponent goes to both the R and the T, so we want to put those together. And remember, we're using 0.0821 for our R because we're doing liter atmospheres or volume and pressure changes times our temperature in Kelvin raised to delta N. So let's look at what delta N would be. So for our reaction, we have 1 mole of gas in the products, 1 plus 1, 2 moles of gas in the reactants. So N would be 1 minus 2, or negative 1. So remember, when our exponent is negative 1, what that actually means is we're going to put it on the bottom of a fraction. Alright, so we can rewrite it like this. 1.67 divided by our R times our T, because it's to the negative 1 power. So 1.67 divided by 0.0821 divided by 500. Alright, so we have 0.0407 for our Kp value. Alright, since we're going from 2 moles of gas down to 1, we're going to see a lower Kp compared to our Kc. If we had an increase in gas moles, we would get a larger Kp value. Alright, let's look at this second one. Here we have solid calcium carbonate producing solid calcium oxide plus CO2 gas. We have a Kp value and a temperature. So we're going to find Kc this time. So my Kp is 2.1 times 10 to the minus 4. Looking for Kc. We're using our R value, and temperature is 1,000. Now, our delta N, we have 1 mole of gas on the product side. We have 0 on the reactant side, so 1 minus 0, which is just 1. So now we can solve for Kc by taking our Kp value and dividing by R and dividing by temperature. So 2.56 to the minus 6. So in this case, since we're producing gas molecules when we didn't have any before, our Kp is a larger value compared to our Kc. And then the last one. We're given Kc and a temperature. Remember, it has to be Kelvin, so we want to convert that first. We can't use Celsius. And we're going to use our equation. So we're finding Kp. Kc is 4.63 times 10 to the minus 3. Our R value times our temperature in Kelvin, so the 298, and our delta N. So now we have 2 moles of gas on the product side because of our coefficient, and 1 mole of gas on the reactant side, so 2 minus 1. Alright, so Kc times R times T. So Kp is 0.113. Producing more moles of gas, our Kp is larger than our Kc value. Looking at the equation, when would Kp equal Kc? So if there's no change in our moles of gas, if delta N is 0, so if delta N equals 0, then our Kp is going to equal our Kc. Because anything raised to the 0 power is 1, so all of this would go away, and Kp would equal Kc. So if we're not changing the amount of gas we have, then our equilibrium expressions would have the same value. Alright, so in this exercise we're going to be looking at reaction direction. Which way does the reaction go? Is it going forward to create more products, or does it need to go in reverse to create more reactants? And we want to use the value of K to determine that. Remember, K represents our equilibrium. And reactions will stay at their equilibrium state unless something happens. So our goal is to get back to this value. So here's our different possibilities. If Q is larger than K, then we need to go to the left. If Q is smaller than K, we're not at equilibrium yet, and we're going to keep going to the right. And if Q is equal to K, then we're at equilibrium. And neither direction is favored. Alright, so let's look at what we have. So the first one, we have H2 plus I2 produces 2HI. Our Kp is 55.3. So Kp means it's measured in atmospheres. So we have atmospheres for each of our values. Alright, so first we're going to write out, right up here, our expression. So 2HI means it's HI squared over H2 times I2. Alright, so let's fill in what we have. Our HI, we have 1 atmosphere squared. For H2, we have 0.2. And for I2, we have 0.0110. Alright, so let's calculate what this is. So at these given conditions, which is not necessarily equilibrium, we're about to find out, we can look at the same ratio to determine if we're at equilibrium. So 1 divided by 0.2 divided by 0.011. Alright, so 454.5. So if this is our Q value, how does it compare to our K? So in this one, Q is larger than K, so we're going to go to the left. Alright, let's look at the second one. 2NO2 goes to N2O4. We have our Kp value of 7. And we have some values for pressure for our NO2 and N2O4. So which direction is this going? Alright, so our Kp is going to be our N2O4 over our NO2 squared. And filling in our values, we have 0.38 over 1.75 squared. So this is going to give us our Q, 0.38 divided by 1.75 squared. Q is 0.124. So let's compare that to K. So if we look over here, Kp is 7. So now Q is much less than K. So this is going to go to the right. We need to make more product. We're not quite at equilibrium yet. And then our last one, CH4 plus Cl2 produces CH3Cl and HCl. Alright, here's our Kp, 1.6 times 10 to the 4th, so a fairly large Kp value. All of these are gases, so they're all going to go into our expression. So CH3Cl times HCl over CH4 times Cl2. Alright, so let's fill in what we have. So over here, 0.25 atmospheres for CH3Cl. HCl is 1.5. On the bottom we have 0.0010 and our Cl 0.035. Alright, so let's see what we have. right, 10,714.2. All right, if we compare it to the KP that we already have, remember this is going to be 16,000. Then our KP is going to be larger. So Q is less than K. We're not quite at equilibrium, so this one's going to go to the right. Right, and the last thing we want to look at with these is manipulations of K based on changing the equation. So if we have a K value for a given equation, and then we alter the equation by multiplying by a cofactor or dividing, or if we flip the reaction, or if we add it to another reaction, we can manipulate the K value as well. It allows us then to calculate a new K value without having to get experimental data. Alright, so let's look at the first manipulation. So compared to this one, in our first example, everything is multiplied by 3. So multiplying by a cofactor means we take the value of the K and raise it to that value. Alright, so if everything is tripled, that 3 becomes the exponent. Alright, so calculating the new K, we have 4.3 times 10 to the minus 25, and we're going to cube that. So 7.95 times 10 to the minus 74. Alright, so multiplying by a cofactor of 3 makes this an incredibly much smaller K value. Alright, let's look at the second one. 2NO goes to N2 plus O2. So compared to what we had up here, this one is just flipped around. So if we have flipped around our expression, we're going to take the reciprocal of the K. Alright, so 1 over our previous K value. And this K value was pretty small in this direction, the original direction. Now when we flip it, going the opposite way, the K value gets much larger. Alright, so very small in one direction means very large in the opposite direction. If we think about what that means in terms of concept, if this direction gives a bigger K value, it means that N2 and O2 gas are the favored components. Alright, I'm going to have more N2 and more O2 gas in an equilibrium mixture. Even when we look up here from our original equation, since the K value is very small, it's going to favor reactants, which are the N2 and O2 gas. Alright, last one we're going to look at, 4NO goes to 2N2 plus 2O2. Alright, so it looks like, based on what I had originally, I've definitely flipped it and multiplied by 2. So I've done two things. So we're going to flip it first. And since I multiplied by a factor of 2, that becomes the exponent. Alright, so I flipped it. That's what I got from being flipped. Now I'm going to square it. 5.4 times 10 to the 48. Alright, so make sure you understand how to do the different manipulations of K. If you multiply by a cofactor, that cofactor becomes an exponent. If you flip the reaction, it becomes the reciprocal. And if multiple things are done, you have to perform multiple functions on the K value too.